Yep. Right. Good evening, fellas. The title for this presentation is Audio Quality in Amateur Radio Transmitters. It's a pretty broad subject, and there are many aspects to it. And I don't honestly think that I can cover all of the topics that one should consider in one presentation. In fact, when I started to think about it, I felt a bit like Elizabeth Taylor's 10th husband on their wedding night. I know what I've got to do, but I'm not sure that I can make it interesting. And that remains to be seen. Anyway, I have decided that I will concentrate largely on two particular topics, and you will see what they are as the presentation continues. First of all, let me say that listening around the bands, it's pretty obvious that some signals are better than others from the point of view of the speech quality. The question is, why is this so? Well, the way I see it, there are probably four particular factors. The first one is the design of the equipment. The second one is the construction of the equipment. The third one is the operation of the equipment. And the fourth one is the maintenance. Now, some of you are probably already thinking, what's he on about? I'm using a Humdinger 123, and everyone knows they have the best audio in the world, and there's nothing I can do about it anyway. So I can't do anything about the design. That's true up to a point. In fact, it's exactly true from your point of view. But things can go wrong. And I am aware of two particular cases where this has happened. One of the very early model transceivers was the Swan 350. And they, given the time, that is to say the particular year, the late 50s or early 60s, it was a fairly significant piece of equipment. It was made for a reasonable sort of a price, although it was beyond most of us. But it did have some specific problems, and these could be attended to. And one of the things I propose to do tonight is to tell you how I was in a position of doing that with two such transceivers. The other transceiver that I want to mention to you is the Atlas 210. Now, it came out with a huge amount of publicity in QST. They gave it a fantastic write-up, and most of what they had to say was confined to a construction of the receiver. And I'd have to admit, it probably had the best signal-to-noise ratio of any piece of receiving equipment that I ever used. It also had a fantastic filter. It was so good, in fact, it was difficult to use because it had picket fence characteristics, and you only had to be slightly off frequency, and there were problems with audio quality. And that happened to be a real problem because of the design of the VFO, which was never mentioned in QST, at least from the point of view of a critique of the VFO, was strictly out of the 1930s. And VFO drift and mechanical changes. The dial, for example, was a cord drive dial, and it used to automatically turn itself depending on the humidity of the environment in which the cord was located. And anyway, I bought one of these in anticipation of a huge improvement in my mobile operation. Up until then, I had only been using homebrew AM gear, and I wanted to move into sideband, and this gear came along, and it got a great write-up, so I bought one. Well, I put it on the air, and immediately started to get some pretty horrible remarks about the audio quality. And initially I was using it from home with an AC power supply, which was absolutely inadequate for the job. So I didn't worry about it too much. I thought, well, I will make a suitable power supply and then I'll rethink the situation. But in the meantime, I started to think a bit more about it, and I realised that there are lots of parts to a transceiver apart from the final amplifier, which is where voltage regulation is a bit of a problem with transistorised gear, because you can go from 100 milliamps to 20 amps peak during modulation. And if you have a power supply that is very poor in the voltage stability area, you've got real problems. Anyway, I thought, hang on, the problem may not be in the final amplifier, perhaps it is somewhere else. And then I thought, well, the most logical place to start looking is in the speech amplifier. So I studied the circuit diagram, and I did not like what I saw. The speech amplifier lineup used an integrated, well, a 14-pin DIL, and on this there were 4 transistors, and 3 of the transistors were used in the speech amplifier. And anyway, I checked it out very simply with a crow and by picking up the microphone and going, which is a powerful sort of a technique if you don't have an audio oscillator, or at any other time. And I found that it was very distorted in the speech amplifier. And I thought, I don't like the design. There were some aspects to it that were very deficient. For example, a typical transistor is like that. You have a load resistor here. You may or may not have a bias resistor here. And you have a forward bias network which has current into the base in that respect. Now, that circuit, which is exactly the way it was used, is not really an amplifier. It's probably more suitable for use as a thermometer, because when the transistor starts to heat up, it draws more current, and suddenly the forward bias circuitry doesn't work properly. A much better type of circuit uses a voltage divider arrangement like that. This system can be made to work if, instead of operating it from there, you take it over and tap it into the load resistor, so that as the transistor draws more current, the voltage here drops and the voltage there drops, so that forward bias drops, and it tends to be a more stable arrangement. So I thought, what I'll do, I'll get hold of one of these quad chips and I'll build up a rough mock-up on Vero board, which I did. I built it up. It worked perfectly. I thought, what's going on? You know, I used the same circuit out of the instruction manual, that deficient design, and it worked perfectly. But the one in my transmitter, it's just absolute distortion. So then where's the cleaner? Oh, here it is. Basically, the design of the transmitter was something like this. You had one amplifier, you had the microphone in here, you had a gain control, that went up to the next amplifier, which went to the next amplifier, like that. And I found that it didn't make any difference where I put the microphone gain control. It was still distorted. In fact, I was putting sine waves in here, and out here I was getting square waves. Like that. And a square wave is the fundamental sine wave plus all the odd order harmonics. So that's why it sounded distorted. And I thought, what on earth is going on here? So I pulled the board out of the transmitter and I examined it carefully, and I found that on the board there were 3 holes. Like that. And nothing in the holes. And I thought, that's strange, why should this be so? Well, then I traced back to where these holes went, and I found that they were in fact these 3 holes here. In other words, the microphone gain control wasn't wired there at all. In fact, it was wired here. So it didn't really matter where I put the microphone gain control. These 2 stages were going full ball, and this one was perfectly capable of driving that one into square wave. So somebody at the factory decided that they would make a minor change. They'd shift the microphone gain control from after the first stage to after the second stage, by which time the damage was done. So that was a design/construction problem. I could never get a specific answer from Atlas as to who made the decision. And all of the transceivers of that particular batch were so wired. Everyone that I heard on the air had this same problem. So you can have a design problem and or a construction problem at the actual factory. And that's what happened to Atlas. That was only one of the things that went wrong with the transceiver. Another one was that in the output stage of the transmitter, it had an RF choke at the centre of the output transformer. It was wound with about 22 gauge wire. And when the transmitter was operated on CW, the peak current in the collector was about 20 amps, at least 10 amps. And trying to run 10 amps through 20 gauge wire, that is a major problem looking to happen. And generally speaking, they finished up with that choke burned out. But the problem was that the voltage drop across that choke was used as a current indication in the final. It was actually a meter shunt. So it needed to be of that order of resistance. A real bad idea. A real bad idea. So I don't think you will ever hear an Atlas transceiver on the air again. They were just an absolute disaster. But QST doesn't accept criticism lightly of American-made equipment. There can be problems with construction. That one that I've just described with the Atlas is typical. Another piece of equipment that I had some dealing with was the Swan 350. I actually worked on 2 of these, and the first one was purchased by a very old friend of mine, the late John Lake, VK2OK, who, anyway, I'll tell you about that later. He bought one of these from a certain amateur, and I knew that the transceiver was a box of junk because I'd heard it on the air before. And when I heard that he was going to buy it, I tried to tell him as politely as I could that was not a good idea. Anyway, he subsequently took delivery of it, and he said to me it looked as though it had been operated in the exhaust vent of a fish shop. It had molten wax throughout where capacitors had suffered temperature problems, paper capacitors. Anyway, I went up there and we worked on it, and we eventually got it fixed. And he was so delighted that he presented me with an RAAF Astro Compass, and I treasured that. But my workshop was broken into about a month ago, and the bastard who did it stole my 2 low-frequency command receivers, and also my RAAF Astro Compass and various other bits and pieces, so it's gone. So if you know of anyone flogging an RAAF Astro Compass in its original sky blue box with a brass base so that it will fit on a conventional camera tripod, you know it's mine. Okay, so now, about 10 kilometres away from me was a very old amateur who had been a great stalwart of the WIA in New South Wales. I think at one time he was president or secretary, and he served for quite a number of years. And I used to hear him working his mates on 80 metres, and I knew that he was using a Swan 350, and the signal was just absolutely awful. So I rang him up and I said, Bill, that rig of yours needs some TLC. If you would not be offended, I'd like to bring over some of my test gear and run the rule over it and see what we can do about it. Oh, he said, I'd love you to do that. I said, okay. Well, we need a new set of tubes. We need some 350 volt 8 and 16 microfarad electrolytics, and a handful of microcapacitors. So we set it up on the bench, operated into a dummy load, and with my trusty old Heathkit oscilloscope, I was able to show him that at the anode of the first tube, it was absolutely riddled with RF. The speech amplifier, because of its design, had a considerable amount of gain, even at HF, and certainly on 80 metres. It was working reasonably well. So I said, look, we've got to get rid of that. So the circuit diagram it had a 12AX7, which is a twin triode in the speech amplifier. Now, typically, a low-level amplifier has a cathode resistor and a bypass capacitor. But when you're only working at very low signal levels, you can get away with a different approach. You can actually use grid-link bias, like that. But you need a very high value grid resistor, about 2 megs. This then relies on a very small amount of grid current in here to develop a voltage at that point. Now, rigs of that vintage were designed for use with crystal microphones. In fact, I think even now, you can't buy an American transceiver with a microphone. For some reason or other, the Yanks don't do it that way. I think because over the years there have been would somebody get me a drink of water, please? So many microphones available in the USA that you were expected to buy your own microphone. And that was part of the problem that I had with the Atlas, by the way. But crystal microphones only develop a very, very low voltage in the order of millivolts. So if you can put millivolts here into this amplifier, and you don't run into problems of overcoming the grid voltage. Thank you. And this is one aspect of the talk that I would like to talk about, but we don't have time. But basically, there is a limit to the amount of voltage you can put in here before you start to run into clipping. But when you have a very low output microphone, it's not a problem. So that wasn't the problem with this amplifier. The real problem was that there was RF coming in here, and RF coming out into the next stage. So the first thing to do is get rid of the RF. Now, I would have to say that the person who designed the 350 did a very good job. There are aspects of it that are quite remarkable. But in the translation into the construction, it lost a little bit. In other words, you look at the circuit diagram and you think, yeah, that's pretty good, that's pretty good, that's pretty good. Except that it doesn't really work very well, because there are aspects that don't show up in the circuit diagram which are important in the construction. In this case, an attempt was made to prevent RF getting into the speech amplifier. The microphone was here. It came out through a resistor. There was a bypass capacitor. And then it went away to the grid. But all of this was so far removed physically from the grid pin of the valve that RF could get in here. And the first thing that we did, we opened up the connection into the grid. God. Okay. Can't see my own. And we put in a grid stopper right at the grid pin. 47k resistor right at the grid pin, and we added a 500 PF capacitor like that down to the cathode connection, so that any RF that got in, this functioned as a low-pass filter basically, which prevented any RF from getting in. So we cleaned up most of it getting in. Now the RF on the anode went from a carrier level of something like that to a carrier level of something like that. In other words, there was very, very little RF getting through the first stage. But we then added another RF bypass down here, and that killed all of the RF getting into the speech amplifier. So I then started looking at the frequency response of the speech amplifier. Now, somewhere about, I think, in the 1930s, the US Army Signal Corps and or the Bell Telephone Laboratories looked at the aspect of how much frequency response you need, what bandwidth do you need in telephone communication. And they came to the conclusion that if you had a passband of 300 to 300 hertz to 3 kilohertz, that was perfectly adequate for both male and female voices. The average male voice is somewhere in the vicinity of here. around about 800 to 1500 hertz. Female voices tend to be higher, and they may extend all the way up to 3 kcs or perhaps even more. Well, the first thing I found with the Swan design, because the amplifier did not have a cathode bypass resistor in the first stage, you couldn't do too much about the low frequency response. In the second stage, the cathode resistor was bypassed with a 0.01 capacitor, and that'd be perfectly okay in the intermediate frequency amplifier of a receiver working at 455 kcs. But at audio frequencies, it's not really enough. What it does, it increases the gain, or allows the gain to become higher at higher frequencies, but drops the gain at lower frequencies. The result was that the bandpass of the amplifier, instead of being 300, was sort of like that. And it was still amplifying up at 10 kilohertz, which you don't need it. So we decided, well, we'll do something about that. So we added a bit more bypassing at the anode of the second valve to reduce the upper frequency limit. So eventually we got the amplifier down to the stage where it was more like that, 300 to 3 kilohertz. So that was a step in the right direction. But then in single sideband, the thing which determines the band pass characteristics of the audio is the placement of the carrier crystal with respect to the filter. If the carrier crystal is out here, you have no low frequency response, the thing will sound very shrill. If the carrier crystal is up in here somewhere, there's no high frequency response, and you may even get residual carrier coming through. Not a desirable characteristic. But depending on the manufacturer's recommendations, the carrier crystal is usually placed at either the 3 dB points or the 6 dB points. What that means here, the 3 dB points means that the magnitude of that compared to that is about 0.7, root 2 on 2. If it's 6 dB, then it's down here at halfway. Now in the Atlas, which has picket fence type filter capacity, it's set at 6 dB. It's more than 20 years since I last did the job on that 350, but I think they call for the 3 dB points, which incidentally the FT7 does. And the FT7 has the most beautiful SSB filter of anything that I've ever seen. It's absolutely symmetrical. And it's exactly 3 kilohertz from the 3 dB points on either side, on the low frequency side and the high frequency side. You could do worse if you were interested in buying a second-hand FT7 and using the filter in a homebrew project, or even using the transceiver in its existing form and following it up with a higher powered amplifier. But one of the characteristics of rigs of this nature is that the carrier crystals tend to drift in frequency, and they may go higher or lower, and you have to adjust them. It's not so much the crystal drifts, but the circuitry around it drifts, because the fixed capacitors that are usually part of the circuit change their characteristics, with the result that the carrier crystal will effectively move, and it needs to be set in the right place. The question then is, how do you do that? Well, the technique which I find is the best technique of all is that you use an audio oscillator to put a signal into the speech amplifier, and then you adjust the the level of the audio coming in so that you get a certain amount of power at that point. In the case of a rig that's going to be used for a male voice, probably about 850 hertz. If it's going to be used by females or other persons with high-pitched voices, then it probably needs to be at about 1000 hertz. You set the levels so that the output from the transmitter is, say, 20 watts. If it's an FT7, you set it at 10 watts. You then move the audio oscillator back and you find the spot where it's down to the 3 dB point or the 6 dB, depending on the rig. If it's not 300 hertz, then you adjust the trimmer on the oscillator circuit to bring it up so that it is at that point. Now, that also shifts this thing, so you've got to go and check it again. And you may have to go backwards and forwards 2 or 3 times, and eventually you'll get to a stage where, in the case of the Atlas, for example, you can have 20 watts there and 5 watts here. And that gives you the right roll-off at the low frequency end. And you have to do this with both sideband crystals. So after you've done it with that one, you go over to the other sideband. If this was the low frequency sideband, and you then want to adjust the high frequency sideband operation, you do the same procedure and you adjust this crystal until you get it so it gives you the reduction that you require, 3 dB or 6 dB. 6 dB means down to a quarter, 3 dB means down to a half power. And that is, when this level is 0.7 of that. That is what we did with build 350. We then went through and we picked up the RF circuits on all bands and checked the neutralisation in the final. To do that, you disconnect the screen voltage on the final amplifier stage after you have previously adjusted everything for maximum power output, and then you fiddle with the neutralising capacitor so that there's 0 RF output from the amplifier. We did that and it worked out quite nicely. Stage of the game, I'd been working on it for hours and I just about exhausted. And I said, okay Bill, we'll have lunch. So he had prepared some lunch, we had lunch, we had a bit of a talk about it. I said, right, I'll go home and I'll give you a call on 80 metres and we'll get you to go through the simple tests. And I said, okay, now first of all, call me on lower sideband, and I listened to it. I said, okay, go to upper sideband, and I listened to it. The speech quality was exactly the same. In each case, the unwanted sideband suppression was higher than I had ever heard a Swan 350 before. It was absolutely magnificent. And I said, righto mate, well you have your skep with your mates this afternoon. Don't tell them that we've been working on the set. Just call them in the normal fashion and see what happens. So I said, I've got things to do, I won't be able to listen. But give me a ring after the Channel 2 news tonight and tell me how you got on. So he rang me up at 7:30 and he said, well, I called them up and immediately they said, what have you done to your rig? We can actually understand you. And I said, well, that's the way it should be. So what I have tried to set out to tell you is that even if the design is okay, even if the construction is okay, the way you operate it can be a problem. In other words, if you're driving the microphone too hard, and I was able to show him how to set the microphone gain control so that he was not overdriving it correctly. There was one thing I failed to mention, that in the process we found that there was quite a lot of residual hum on the carrier. Now the 350 uses a very interesting balance modulator circuit. It uses a rather special sort of tube which really bears some relationship to a cathode ray tube in design and construction. I've forgotten exactly what it's called now. I think it's a 8073 or something like that. Some of you might know it. But it's a very special tube. It has two anodes. It has two deflecting electrodes. It has a grid. And it has a cathode. And the way it works, one of these deflecting electrodes basically is operated by this arrangement, which is usually called a potentiometer. It gives a fixed voltage on it. The other one has the audio frequency energy applied to it, and the carrier oscillator is supplied via the grid. And the basic idea is that the anodes are operated in push-pull, like that, centre tapped, and a considerable amount of effort was put into making the whole circuit balanced from both the point of view of DC and AC. And if you are building equipment, I would like you to accept as a basic premise that the first thing you have to do is to make sure that the DC operating conditions are correct. If the DC operating conditions are not correct, you can forget trying to adjust the thing and try to make it do what it's supposed to do. If the DC operating conditions are not correct, then there's probably something wrong. So that's the first thing you have to find out. Anyway, we found that the carrier balance was achieved by a potentiometer arrangement and these were connected to the two deflecting electrodes via, sorry fellas, I can't see very well, via various balancing resistors and isolating resistors. This is a greatly simplified version of the circuit. And you adjust the carrier balance by adjusting this circuit. This thing works a bit like a cathode ray tube. Electrons go out like that, and depending on how these electrodes are, what voltage is applied to them, you can unbalance the carrier and produce output. Now this one is constant. And I found that there was quite a lot of hum on that electrode. We balanced the carrier right down to the lowest possible level. But what we were then getting were two hum sidebands, which were quite objectionable. So the first thing that I did was to put another decoupling resistor in there and add more bypassing, about 32 microfarads of electrolytic capacitor. And that reduced the hum on that electrode quite a lot. But there was still more. And I thought, where is it coming from? No, it's not on the audio coming in. And I thought, ding, it's got to be heater cathode leakage. So what we did then, we put in a half-wave rectifier and operated the heater, instead of operating it from 6 volts AC, we operated it from DC by putting in a half-wave rectifier and a heck of a lot of capacity, so that the voltage on the heater, instead of being like this, was probably more like this. So that was the order of ripple now in comparison with that. And we got the hum on the residual carrier balanced down to the lowest possible level. So it was absolutely T9 DC, a beautiful carrier for use on CW. So we were able to improve the performance of the set on CW. Anyway, I went home and called him up and I said, okay, let's hear the lower sideband. Now let's hear the upper sideband. Okay, now balance the carrier down to 0. Turn the microphone gain control down to 0 and let me listen. I couldn't hear any carrier. I said, okay, now just unbalance the carrier slightly so that you've got a small amount of plate current increment in the final amplifier indicating there's power coming out, and I listened to it and the tone was perfect. So, as I said earlier, he made contact with his friends that night, and the thing sounded so good that if you had been told that it was a Collins S line, you would have been prepared to believe it. So that's something that you can do. The fact that something has been designed well doesn't necessarily mean that it's going to work incredibly well, particularly if it's no longer a young piece of equipment. Operation. I was able to show him how to correctly set the microphone gain control so that he didn't overdrive it. When the FT897s first appeared in this country, just about everyone got yelled at, turn the gain down, turn the gain down, because for some reason or other, and it's been put to me that in Japan, because the houses are so small and the hams don't necessarily have a ham shack, they might have a corner of a room, they have to be able to speak very quietly into the microphone. So the microphone gain level is set at a very high value. But anyway, when they arrived in Australia, they were all being grossly overdriven. And once people who were doing this were instructed and how to turn the microphone gain down, they suddenly appeared as being a very, very nice piece of audio gear. And those of you who've heard 897s from time to time will know what I'm talking about. Maintenance. Okay. You buy a piece of gear, it's new, and eventually it's not new. Things happen. Resistors heat up. They change their value. Capacitors nowadays are much more reliable than they were in the days of the ones which were called Duke-on batteries. They got that name because certain paper capacitors, due to electrolytic action inside the foil, could develop a quarter of a volt of DC on their own account. And when they were used as coupling capacitors, they caused problems. Some of you may remember black and white television, and it was not unusual if you were visiting somebody who had a black and white TV set to find that at the bottom of the screen there was a great big fold over. Usually it was described by the sections of the family who have to be obeyed. It would be described as a white line. You'd have a here's your picture. And then down here, there was this thing, and sometimes it would be black underneath that. And that was usually caused by leakage of the coupling capacitor in the vertical output stage, which was usually, I think, about a 0.05 microfarad paper capacitor. When Philips brought out their polyester capacitors, their 400 volt polyester capacitors, the whole industry went through a huge leap. Suddenly this effect disappeared because there were no longer leaky capacitors being used. So that's one aspect of maintenance which needs to be looked at. the effect of yonky old capacitors. And that was okay in the valves of valve sockets and point-to-point wiring and so on. But nowadays, with flow-soldered printed circuit boards and components that are put in place with lead-free solder, it's not all that easy. Not all that easy. If you've got, first of all, you've got to find which is the appropriate defective capacitor. And then you have to change it, and that's the hard part. Probably the best way to go about it is, let's say there's a connection there and you have a capacitor, something like that. The best way is to cut it in both places and remove the defective component. The defective component, for example, could be a 14-pin dill, in which case you've got to cut 14 leads. And then you use a solder sucker and a pencil soldering iron to remove the little bits of lead that were hanging out initially. If you try to take the thing out one at a time, you'll probably finish up damaging the board. But this way, you do a minimum amount of soldering on the board. You just take out the whole defective component and then clean out the little leads with a pair of needle-pointed pliers. You heat the pad, pull it out, or even sometimes you can flick it like that and it will fall out. So that's one way of looking at that. So far I've combined my remarks to single sideband, which is the mode that is probably most popular, but it's not the only mode. And there are some people who still like to use AM, and there are certain characteristics which you have to achieve. In other words, you have to build the RF part of the transmitter which delivers the carrier wave. Viewed on the oscilloscope, the carrier wave looks like that. It's all filled in. Under modulated conditions, ideally speaking, this should double in height. If you put a sine wave into the modulator, this should double in height, like that, and it should come down just to zero on the next crossover. Let's see what I'm doing here. Anyway, that's the idea. If you're over-modulating, that won't happen. You will get something like this. And when you get to that stage, the carrier is completely cut off, just as effectively as if you were using a Morse key and thumping it on and off. And that causes an enormous amount of interference on the adjacent channels, and perhaps even quite some distance away, particularly to someone who is in your near vicinity. So to achieve this, the modulator needs to be able to provide enough power to double it on positive peaks, and the gain control needs to be set so that you do not cut off the carrier on the negative peaks of the modulating cycle. And that's the object, that's the aim of the exercise. You can do it very easily with a crow. You can try to do it without a crow, and somebody will tell you it's not enough, somebody else will tell you it's too much, and it's all very confusing. But if you really want to be using AM, you need to have sufficient instrumentation to be able to set it up properly, and the minimum is a crow. It does not need to be an elaborate crow. as long as you can get access to the vertical plates on the crow, even a relatively inexpensive crow like the old Heathkit is perfectly adequate. Now let's talk about FM. It really shifts around. If you listen to an FM signal with the receiver switched to the sideband mode, you can hear the carrier shifting, you can hear the beat frequency changing. You need to adjust the microphone gain control so that at full output from the microphone, you are just filling the pass band of the receiver. If it doesn't fill the pass band of the receiver, the audio will sound weak. If, on the other hand, you drive it outside the pass band, what happens is the carrier will be cut off in much the same way as it was in the AM situation, and it sounds as though somebody's pumping it on and off with a Morse key, and it will produce a distorted signal, and it will sound pretty awful. So you need to be able to adjust the microphone gain control so that it just fills the pass band. Most of the modern rigs have a form of microprocessor control. You have to go into the memory, into the menu, and you'll find a menu level where it says FM mic gain. And then you adjust that, and you ask a number of people, and you hope for the best that you get honest reports, which will enable you to find this position. Again, when the FT897 arrived, most of them were set so that the microphone gain control was in about the 100 level on the screen, on the menu level. But depending on the volume of the speaker's voice and the way in which they held the microphone, probably somewhere no more than 30 was about right. And it took quite a while to persuade some people to actually turn it down to that level. And the other thing is that when you're using a microphone, you have to adopt a standard procedure. If you're attempting to use it while you're waving it around like this or talking like that, it doesn't work. You need to hold it in a fixed position. With most amateur radio microphones, I have found that if you hold it in the left hand, and most of them are designed for right-hand people, so they hold the microphone in the left hand, and they just hold it against the face like that, you can maintain the position all the time. You can always have the microphone in the same place. You then talk across the face of it, not into it like that. And yelling into it like that might be the done thing in certain other frequencies, but it's not the way to do it in amateur radio. So, I've discussed the possibilities caused by design, by construction, by operation, and maintenance. If you have modern equipment, and most of us do have nowadays, it's chock-a-block full of electrolytic capacitors. Now the US Air Force says that an electrolytic capacitor which is not used for 2 years should be regarded as a replaceable item. So if you have a number of transceivers, it's a jolly good idea to cycle through them so that you use each one, from time to time, and don't leave one in the cupboard for 10 years and then pull it out and think, oh, it's time I tried the old one, It probably won't work. Some time ago I worked a fellow on 40 metre CW, and the transmitter had a terrible note. It was about probably T7 instead of T9. It was not a pure DC note, it was quite rough. And I said to him, look, you've got a problem. And I knew he wasn't listening, but I happened to know a friend of his, and I rang up this friend and I said, XYZ's got a problem with his transmitter. Could you take over an oscilloscope and have a look at it? Well, the real problem, of course, was the power supply. It hadn't been used for yonks. The electrolytic capacitors in it had well and truly dried out, and whereas it's supposed to have 14 volts DC with no ripple, it had about 10 volts DC with plus or minus about 4 volts of ripple. And the next time I worked in, he had a beautiful DC signal, beautiful tone. And I said, "What did you do to the rig?" He said, "Oh, I didn't do anything to the rig, it was the power supply." I said, "Oh, yeah, how did you fix it?" "Oh," he said, "I threw it away. I had another one." And I thought, okay, it might have been easier to fix it, but, you know, he was able to fix the actual result. In other words, get himself a decent signal again by using a power supply which was free of ripple. Now, look, I'll just take a little look at my notes to see if there's anything that I've forgotten. If you'll just be with me. I did mention the placement of the carrier crystals, and I explained how best to set them. Did everybody understand what I was telling you about then, or would you like me to go through that again? Don't all speak at once. Okay, I'll take that as... I'm not sure whether I should take it as meaning you understand or whether you didn't.
I followed it. That's good. I think I followed it, Max.
Okay, is there anyone who is not desperately sure what I was talking about? Because I don't mind going through it again. It is important and you need to understand. Okay, in that case, unless there are any questions, I'll fold up my tent.
I was just going to ask a question then, just on that.
Oh, there's a question.
Yeah. Just okay.
He's folded up his tent, bit late.
Sorry, okay, all right then. Yeah, no, the question I was going to ask about this carrier crystal is, okay, all right, when you've got these modern rigs, what can you do about it? I mean, it seems that adjusting the carrier crystal appears to me to be an issue that you can deal with the older equipment, but the modern stuff, the 857s and all that sort of stuff, what can you do there? Anything?
The very modern stuff, unfortunately, is microprocessor controlled. And you have a menu level which enables you to move the carrier crystal using the menu. But if you're referring to the type which just use standard quartz crystals, then you've got to find the appropriate trimmer and alter it. If the crystal has totally failed, and that's not unusual for that to happen, because usually the crystal consists of a quartz plate, silver plating on either side, and a spring which is soldered onto the silver plating. I don't know whether you've ever tried to resolder one, but please don't do it, because you'll then have a crystal that's no good for anything. Been there, done that. So the best way is probably to throw that crystal away, order a new one. The next question, of course, is how is it soldered onto the board? And if it's using lead-free solder, solder suckers and all the other things are about the only way you can go, I suppose. I would not like to be there, but fortunately, most of the rigs that I've had were older style ones which were soldered with genuine solder, and it was not a problem. So if you do have that problem, well, you just have to analyse it and come up with a result. Probably the best way is to cut the leads, as I explained, use the solder sucker or just melt the solder through the board like that without letting go of it. And hopefully the wire will then come out and you'll still have the board in your hand. Any other questions, please? Okay.
Thanks, Max. That was great. That's perfect, Max. Thanks. All right.